Today is going to be our first day of an introduction to transformers, and we're not even really going to talk about transformers at all.
Oh, look, I have two of them.
All right. So this is our big overarching topic for the next few class meetings. What we're going to be kicking things off with here first is the concept of flux linkages, inductance, and energy. So I briefly talked about Faraday's law of induction in class on Tuesday. I don't think I gave you guys any math or anything involved with it, but it was mentioned when we were talking about eddy currents. Effectively, anytime we have a time varying current, we have a time varying magnetic flux, and that time varying magnetic flux tends to induce voltages in currents in conductors. Okay. So mathematically, Faraday's law of induction says that the induced MMF, or excuse me, EMF, sorry, got too used to magnetic things, is equal to the closed line integral of E dot dl, which that's just the definition of a voltage, really. And that's going to be equal to negative the derivative with respect to time of the surface integral of the magnetic flux density B dotted into some differential area element A. Okay, so this is the big picture math definition that we are literally never going to use. All right, so instead, we're going to look at what this thing is. Okay, so the left-hand side and the middle bit is effectively just saying the induced voltage. Okay, so our induced voltage, or our induced electromotive force, is going to be equal to the right-hand side. So if we didn't have that negative d by dt bit there, that's just the integral of B dotted into some differential area. That is literally our definition for flux that we introduced on the first day of class. Okay, so we can call this EMF induced as negative N times the derivative of the magnetic flux as a function of time. And this is sometimes expressed as the derivative of lambda with respect to time. And from this, we can see that lambda, which is our flux linkage, is simply equal to N times phi B, where N is the number of turns that the flux is passing through, and phi B is the flux. Okay. So the flux linkage is also related to another important quantity called the inductance. Okay. So this is, let me put a box around this guy because this is an important equation that we're going to see and use a lot. And then the next important equation that we're going to use a lot is that lambda, our flux linkage, is equal to L, our inductance, times I, which is the current causing the flux. And this guy right here can be rearranged pretty simply to show that inductance is then going to be flux linkage divided by current, or N by B divided by current. And we can go a little bit further here if we so chose. Sorry. So, yes, ma'am. The lambda? This is lambda. Okay. Oh, okay. So kind of like a mathematical therefore kind of thing. So like we said that the induced EMF was equal to the derivative of the flux linkage with respect to time. And based on the previous expression, we were able to develop a equation for flux linkage as lambda, the flux linkage, is equal to N times phi B. One other thing that I want to talk about real quick here, just because none of you have asked about it, is what the hell happened to the negative sign? So Faraday's law is up there, but we also have to take into account what's called Lenz's law. Lenz's law simply states that nature abhors a change in flux. We talked about this a little bit last time, right? So if we have a time varying flux in one particular direction, the induced flux will be in the opposite direction to try to keep that flux constant. That's all that negative sign is trying to do. That's its job. Okay. All right. So using Ohm's law for magnetic circuits, which, just to be clear, is this guy that says Ni, our magnetomotive force, is equal to our magnetic flux times our reluctance. If we rearrange this expression for flux, what we're going to find is that we're going to have, let's see, phi B is equal to Ni over R. So this would look like N over I times Ni over reluctance. The i's cancel each other out, and we have N squared divided by the reluctance. So if we ever need to figure out the inductance, it's just going to be related to some square of turns ratios, or I'm going to back that up a little bit. It's going to be two turns ratios multiplied by each other and then divided by some reluctance. The reason why I back that up a little bit is because we're going to see a thing called mutual inductance, where it's not going to be the same turns ratio multiplied by itself. Yes, sir. So capital I is a DC current and lowercase I is a time varying current. That's it. All right. So we've introduced the concepts of flux linkage and we've introduced the concept of inductance. Now let's look at a simple magnetic circuit. Okay. So let's say that we have drawing my core material. I've been using blue, so I'll get back to doing that. So let's say that we have a core that looks like this. Where, let me put something on here real quick. This length that I've outlined here is going to be our core length. We're skipping ahead and not making you guys calculate all of that kind of stuff. Let's say that it is 30 centimeters. Our core has a cross-sectional area of 9 centimeters squared. And our air gap here LG is half of a millimeter. So just one thing that I want to point out here. We are going to work this problem since LG is very, very small. We are going to assume that the cross-sectional area seen by the flux in our air gap is the same as the cross-sectional area of the core. Effectively, we're saying our gap is so small, the flux doesn't really have an opportunity to spread out much. Okay. All right. We are going to wrap a wire around our core, like so. And we are provided the following information, okay? So our core is going to be made of M5 steel. We're not going to use a table. For a magnetic field or magnetic flux density strength of B is equal to 1.0 Tesla. We have a permeability of 72,300 times mu naught. And for a magnetic flux density of 1.8 Tesla, we have a core permeability of 2,900 times mu naught. So instead of making us calculate the permeability by looking at B divided by H at a table, I'm just giving you the numbers. Yes, Casey. It's approximately equal to AC. So I want us to determine the equivalent reluctance seen by our coil. Let's see, did I give you the number of turns? I must have, yeah. So N is equal to 500. So the equivalent reluctance at both permeabilities and the equivalent inductance at both permeabilities. So for our core permeability of 72,300 mu naught, we are going to have our core reluctance, which is going to be simply LC divided by mu C AC, right? So LC was 30 centimeters. Mu C 72,300 times 4 pi, excuse me. Times 10 to the minus 9 henries per centimeter times our 9 centimeters squared. And we get 3.669 times 10 to the 3 amp turns per Weber. For our gaps, we're going to have LG over mu naught times AC. Again, we're assuming that the fringing is negligible, so we don't need to change our cross-sectional area seen by the flux. So this is going to look like half 0.05 centimeters, half a millimeter over 4 pi times 10 to the minus 9 henries per centimeter times 9 centimeters squared. And we get 4.421 times 10 to the 5 amp turns per Weber. And the equivalent reluctance is then RC plus RG is 4.458 times 10 to the 5 amp turns per Weber. And finally, our equivalent inductance, LEQ, sorry, is going to be N squared over REQ, or 500 turns quantity squared divided by 4.458 times 10 to the 5 amp turns per Weber. And this comes out to be 0.561 Henry, where a Henry is nothing more than a Weber per ampere. Yes, ma'am. That's correct. That's the reluctance of the air gap. So, right. So in previous examples, we had a large air gap, and I say large because it was, let me do something here to explain why I'm saying that AC is approximately equal to AG. Okay. So if we have a very small air gap, these light blue lines are our flux lines, right? So our flux is going to spread out a little bit, but it's not going to be a whole heck of a lot. So if we don't allow our flux to spread out a lot, the cross-sectional area seen by the flux in the air gap is going to be effectively the same as the cross-sectional area of the core. So the smaller our air gap is, the more the cross-sectional area seen by the air gap, or the cross-sectional area of the air gap looks like the cross-sectional area of the core. So we are making an assumption here, and I pointed it out up here, that since our gap is very small, half a millimeter, that's not going to be a large enough gap to allow our flux to spread out. So that's why we're not modifying AG like we have done in previous examples. I'm sorry, what? 500, sorry. My penmanship is bad there. Let me put that. 500 turns. And let me erase all this junk right here because we talked about that previously. All right. So now let's look at what happens when our core permeability is that 2900 mu naught. So let me ask you guys, I guess, a simple question. What are we expecting to happen here? Anybody have any thoughts? I'm sorry, what was that? So if the bottom is going to, if the denominator is going to increase, or excuse me, decrease because mu is going down significantly, then that should mean that the reluctance, at least of the core, is going to go up, right? So right now, with a very high permeability core, we see that the air gap is a much larger contributor to the overall reluctance, right? As our permeability goes down, we should see that the reluctance of the core is going to increase relative to the air gap, and so it's going to make more of a difference. So for our core, we're going to have the exact same equation, LC over mu C AC, but we're using a new value for mu C. So let me just write this down really quickly. 30 centimeters times 2,900. 4 pi times 10 to the minus 9 henries per centimeter times our cross-sectional area, 9 centimeters squared. That's going to give us 9.147 times 10 to the 4 amp turns per Weber. Is the reluctance of our air gap going to change because our core permeability changed? Not at all. So RG is going to be the exact same thing. 4.421 times 10 to the 5 amp turns, excuse me, per Weber. And our equivalent reluctance is then simply RC plus RG. Which is going to look like 5.336 times 10 to the 5 amp turns per Weber. Pardon me, giving us an equivalent inductance at this particular permeability of N squared over REQ, which will be 500 turns squared divided by that 5.336 times 10 to the 5 amp turns per Weber, or 0.468 Henry. So what did we observe here? Our permeability was changed by a huge amount because we were at a different part of our magnetizing curve effectively, right? So at our first calculation, we had a magnetic flux density of 1 Tesla, and we were in that linear portion of our magnetizing curve, and we had a relative permeability of 72,300, I believe, if I'm remembering the number correctly. Yeah. At our second calculation, where we were at 1.8 Tesla as our magnetic flux density, we were very likely somewhere either in the knee or in the actually definitely in the knee area, or the permeability would have been even smaller. But we were in the knee area of that magnetizing curve, and we saw that our reluctance, excuse me, our permeability was much smaller, but we didn't see a huge change in the inductance, right? So our inductance when mu was 72,000 was half a or 0.561 Henry. And when our permeability was 2,900, our inductance only dropped to 0.468 Henry. So what is the air gap doing in this case? The air gap is effectively serving to linearize the inductance. So the inclusion of the air gap is what's causing the inductance value to not change by nearly as much as the core permeability is changing, which is the reason why we put air gaps in magnetic circuits. It keeps our inductance relatively linear. Okay. All right. So now let's break things a little bit. Or not really break things. Let's introduce an increased level of difficulty. I know you guys are thrilled by adding another coil to our system. Okay. So let's say that we have a similar core. Like so. This distance right here is LG. And then this distance is the total flux path or the average flux path length of our core. And let's say that I wrap a wire around this core that has N1 turns, where my current I1 is flowing in this direction. And then I put a wire over here. And I wrap it around my core some number of times. Let's call that N2, like so. And just to make our math easier, let's say that the permeability of our core material is infinitely large. Effectively, we're saying the core isn't going to contribute any reluctance here. Okay. We're just doing this so that I can do algebra and show you what the relationships are when we work problems, and where we're going to work one in a bit. We'll see what a real permeability has to do with things here. Okay. All right. So let me ask you guys a question. So we're assuming I1 is wrapped around the coil. Let me draw it a little bit better here to try to illustrate what I'm talking about. So if we're looking at just the section of the core over here, on the left, what should the direction of my magnetic flux be? Use the right hand rule. Up. So that coil I1 is going to be generating some flux up. Okay. Now, if I draw a section of the core that we see over on the right-hand side, and I wrap my wire around it, This is I2. And there are N2 number of turns. What's the direction of my flux? Down. So from a magnetic circuit perspective, okay, what I have is something like this. Here's MMF of coil 1, which is just N1 times I1. I have the reluctance of my air gap, RG, which is going to be mu naught times A G over LG. And then over here, I have my MMF2. That is just, excuse me, this should be N1 I1. This is going to be N2 I2. Like so. And this guy is going to push some flux. I'm going to call it B1 around in this direction. And this guy is going to push some flux B2 in this direction. Okay. So we're going to get into a little bit more detail about the concept of inductance here by really digging into what the flux linkage means. Okay. So the flux linkage for coil 1, I1, is effectively just the number of turns that coil 1 has, which is N1, times the total amount of flux that's flowing through that coil, right? The total amount of flux. So I'm going to put here phi total. And we could see that that's going to be N1 times flux 1 plus flux 2. So what is flux 1 going to be? Anybody have any thoughts on that or how we might figure it out? So what if MMF2 were totally off? That coil did not exist, or that coil wasn't passing a current through it or anything like that. How would we figure out what our flux 1 is? So flux is equal to MMF over our reluctance. Absolutely right. So our MMF is N1 I1. Our reluctance, the only reluctance we have in this whole thing, is mu naught AG over LG. So if we take the reciprocal of that, we're going to have LG over mu naught AG. So that's what flux 1 looks like. And now let's figure out what flux 2 is. And let's do the same thing here, okay? So by that I mean, we're going to effectively turn off coil 1 so that MMF1 is 0. Allison, are you raising your hand? Oh, nope, nope, nope. You are right. And so I have this upside down. So nope, you're 100% right. I had it upside down and I did not notice. So thank you very, very much for pointing that out. You are 100% correct. All right. So thank you again for pointing that out. Now let's get back to the question at hand. What is the flux by 2 if our coil 1 is off? It won't be the same thing. It'll be real similar though, right? Because it'll be N2 times I2 mu naught AC over LG. Okay. So why LG? Because the gap is the only thing that has any reluctance. Oh, sorry, that should be AG. Thank you for that. Sorry. My nose is itching and I'm sleepy and I'm distracted. So thank you very much. I genuinely want you guys to point out when I make mistakes. So thank you. Apparently 3 cups of coffee isn't enough to get me through noon today. Yeah. Goodness gracious. So we're going to do a little bit more annoying algebra here. So what we're going to have is N1 squared times a factor of mu naught AG over LG times I1 plus a factor of N1 times N2 times mu naught AG over LG times I2. Okay. So let me scroll up here a smidge where we defined the concept of inductance. Flux linkage is equal to inductance times the current that's causing the flux. Okay. So this is going to be L11 times I1 plus L21 times I2, where L11 is the self-inductance because we're seeing how much flux is passing through coil 1 caused by current I1. And L21 is what we're going to call our mutual inductance. So it's related to how much how much flux is flowing through coil 2 because of the MMF in coil 1 or vice versa. Okay. But since we're looking at flux linkage 1 here, so this is going to be specifically, let me write this down. The flux that is created by coil 2 that is passing through coil 1. And we could do a similar derivation for our flux linkage for coil 2, so we'd have some lambda 2 and we'd get something extraordinarily similar. In fact, we would have this term here for sure, but we'd have N2 squared mu naught Ag over Lg for the other term, okay? So this is self-inductance and mutual inductance. This self-inductance is literally the exact same thing that we were calculating up here, okay? So that's always just going to be the number of turns squared divided by the equivalent reluctance seen by that particular coil. Self-inductance is the easy part. Mutual inductance is going to be the thing that is potentially quite a pain in the butt. And so let's take a look at that by working out a problem. Okay. So I have the following circuit or magnetic circuit. And I want to tell you guys something here real quick. The in-class assignment for today is related to this particular magnetic circuit. It is, I sincerely hope, the only time I'm going to be this quote unquote mean to you guys with this type of problem. Everything else that I ask you guys to do should be significantly more straightforward than what we're about to do here. And if it's not, or if you don't believe it is, tell me and call me a jerk, and I will take your remark to heart and try to make it easier on you. All right, so let's define some quantities here. So let's call this length L1. Let's call this length L2. Let's call this length L3. And this length LG. And then we have the same width all around this magnetic circuit. Do it over here. And same thickness as well. So let's define some things here. So let's say that L1 is 60 centimeters. L2 is 40 centimeters. L3 is 10 centimeters. LG is 1 centimeter. Let's say that our width is 5 centimeters. Our thickness is 5 centimeters. And our core has a permeability of 5,000 times mu naught. Let's wind some coils around this guy. So our first coil is going to be here. We have some number of turns NA. The little arrow is the direction of our current, and I'm going to call this current IA, like so. We're going to have a coil down here. That has NB turns and is carrying a current of IB. And then we have a coil over here. carrying a current of IC with NC turns. And let's say that NA is equal to 100 and B is 200 and NC is 500. I want us to determine 4 pieces of information together. And then your in-class assignment will be figuring out 1 piece of information on your own, okay? So what we're going to figure out together is the self-inductance of coil A, the self-inductance of coil B, the self-inductance of coil C, and the mutual inductance. Did I call this L or M earlier? L. Okay, we'll keep on trucking with L then. Between coils A and B. So I just want to make you guys aware on the in-class assignment thing that I'm giving you guys today. I designated the mutual inductance as MBC. So you might see mutual inductance as M and self-inductance as L. Another way that you can see it, self-inductance is the same subscript repeated, mutual inductance is different subscripts. So LAA is going to be a self-inductance, LAB is going to be a mutual inductance. So sorry for using multiple different ways to express the same thing on the same day. I understand how that can be rather confusing. To me, as an electrical engineer, V is voltage or velocity, and there's not going to be a lot of times we're going to see both of those.
You're already over.
All right. So I haven't given you guys, a huge amount of problems to this point where we've had to actually use circuit analysis techniques to figure things out. This is going to be one of those. All right. So the first thing that I'm going to do is I am going to draw an actual circuit for this guy. So this is what my circuit look like. I want to make sure that you guys understand the polarities that I've chosen for my MMF sources here, okay? So this guy here in the middle is the MMF generated by coil A. And I chose the positive polarity on top because the arrow is on top effectively, okay? Now, this guy over here on the left-hand side is the MMF that's generated by coil B, okay? So using the same convention that I did for coil A, we could have put that MMF there with that particular polarity, but I simply slid it up that leg to make the circuit look nicer to me, okay? So that's why the positive polarity is on top there. Similarly, if we look at the MMF for coil C, I could have drawn that one like this, because the positive, the arrow was on the left-hand side, so the positive polarity terminal was on the left-hand side. And when I slide it up the right-hand leg of this thing, that's going to make it put the positive polarity on bottom. So I just wanted to be very clear about where all those polarities are coming from. All right, so we all seem to be catching what I'm throwing. So now let's label all of these reluctances. So let's call this R top left, R top right, R left, R right, R top middle, R gap or RG, R bottom middle, R bottom left, and R bottom right. So for the next 10-ish minutes, hopefully not too much longer than that, what we're doing is effectively the same damn thing we've been doing since I've been in this classroom, simply calculating reluctances and all that kind of jazz and putting things together. So we can say, I hope pretty easily, that R top left will be the exact same thing as R top right, will be the exact same thing as R bottom left, will be the exact same thing as R bottom right, because they all have the same length, they all have the same permeability, and they all have the same cross-sectional area. So that's going to look like L 1/2 of L1 minus W over mu C WT. And throw this out here real quick, 5,000 times 4 pi times 10 to the minus 9 henries per centimeter times 5 centimeter times 5 centimeter. And up here we have 1/2 60 centimeters minus 5 centimeters. 1.592 times 10 to the 4 amp turns per Weber. Okay, so for these next ones, I would like to not substitute in the numbers just because it's taking us time to write that kind of stuff down. And we've done these equations, calculations so many times at this point. I don't think you need to see it 7 times right now, okay? So we can see that RL will be equal to RR. That's going to be L2 minus W over mu C WT. And that comes out to be 2.228 times 10 to the 4 amp turns per Weber. Then we have our top middle. So what's the length of this top middle branch? And so let me specify here. I'm talking about the distance from this point to this point in terms of the other things that I gave you. Minus W, yes, so L2 minus L3 minus LG minus W. You guys nailed it, awesome. All right, and that's going to look like 1.528 times 10 to the 4 amp turns per Weber. Then we have our gap. RG is going to look like LG over mu naught W plus LG times T plus LG. Let's see, 2.210 times 10 to the 6 amp turns per Weber. And finally, our bottom middle is going to look like L3 plus half of a width divided by mu C WT. And that guy comes out to be 7.958 times 10 to the 3 amp turns per Weber. Okay, so what I'm going to do from all of those pieces of information is I'm going to lump things together here. So let's talk about that really quickly. RTL, RL, and RBL are all connected in series. Anybody have a problem with that? Yes. So we're looking at this distance right here, okay? So the distance from here to here is L3. And the, shit, I didn't mean to erase that, sorry. And then we have to add this little distance between those two things, which is exactly 1/2 of a W. So that's why it's L3 plus half of a W. Okay, so let's look at it from here to here is what I'm calling L2, right? From here to here is L2 minus W. Okay, because we're taking half a W off the top side and half of a W off the bottom side. Are we okay with that? Okay. Now, we have this L3 thing right here that's problematic as well. So we have this dimension is L3. So when we were trying to find this dimension right here, let me put this in, this is our gap length, right? This bit right here is L2 minus W minus a gap length minus L3. Okay. Now, if we're looking at just that's how we got it for top middle. Okay. So we have this dimension here. That is L3. And then we have this other dimension here. That is half a width. And so when we add those together, we get L3 plus half a width as the flux path through this section right here. It's okay. It's not a problem at all, okay? So I am trying to find, I don't know if a different color is going to help, but I'm trying to find just this length, okay? So next to it, we have L3, and then a little bit more than L3. And that little bit more is exactly 1/2 of the width. So from here down to here is L2.
Wait, oops. Okay, so for RV, right, it's
For RBM, we're just looking at this short length right here. So we are given the length of how far that little stub sticks up. That's L3. But the total length that the flux passes through along that path is all of that L3 plus half of a W. All right. Okay, so circling back around to what I was talking about a moment ago, we are putting the resistor, or excuse me, the reluctance RTL in series with the reluctance L in series with the reluctance RBL, or they are all in series, and we're going to combine them into a single equivalent reluctance. So we are going to have some reluctance R left, that is RTL plus RL plus RBL, and that comes out to be 5.411 times 10 to the 4 amp turns per Weber. We scroll back up here really quickly. We can see that RTM, RG, and RBM are all in series, so we can lump those guys together. So let's just call that middle, or R mid. So TM plus RG plus RBM, and that comes out to be 2.234. I must have made a I definitely made a mistake there with the exponent in my thing. I have it as 2.234 times 10 to the 4. Would somebody verify? I think it's supposed to be 2.234 times 10 to the 6. It shouldn't be smaller than the other ones because it contains the air gap contribution. All right, so let me just do this really quickly. So we're talking about TM, so 1.528 times 10 to the 4 plus G 2.210 times 10 to the 6 plus 7.958 times 10 to the 3, 2.233 1, 2, 3 times 10 to the 6. Okay. And then lastly, we have that right hand path. That is going to be R top right plus R plus R BR, and that should be the exact same thing as R left because our magnetic circuit is symmetrical. So 5.411 times 10 to the 4 amp turns per Weber. All right. So I'm using these three new reluctances to redraw my equivalent circuit in a way that's a little less of a pain in the butt to look at, okay? So my new version of my equivalent circuit is going to be this guy. Here's MMFB, here's R left. Here's R mid with MMFA. Here's R right and MMFC. Are we all okay with this simplification of our magnetic circuit. Yeah, after we found what all of those smaller pieces are, we lumped everything that was in series together with each other, and we came up with this relationship, which should be a little bit easier for us to analyze when we're having to calculate flux and things like that. Okay. So what is the equivalent reluctance seen by coil A? Use these three reluctances and tell me what it's going to be. So to be clear here, we have R left, R mid, and R right, like so. We're looking in through those open circuit terminals and finding out what the reluctance is going to be. So what does it look like? R mid in series with R left in parallel with R right. And numerically, to me, that comes out to be 2.261 times 10 to the 6. Amps per Weber, where I'm assuming I calculated this right. I actually might double check that really quickly. So R mid. Oh no, that's definitely right, because it's the air gap is dominating everything. That's why it's that large. Nope, that seems fine. Okay. I'm sorry, what? Oh, amp turns. So turn is a dimensionless quantity, so if I ever forget amp turns, it doesn't matter. Yeah. In my notes, I just have it written as amps per Weber. In my old notes, I just have it as written as per Henry's, but yeah, so I apologize if I'm playing fast and loose with the units when I do not want you guys to do that. So thank you for the correction. All right, so since we know the equivalent reluctance seen by coil A, it's pretty easy for us to figure out the equivalent inductance seen by coil A, right? So that's just going to be the number of turns in coil A squared divided by the equivalent reluctance seen by coil A. So substituting in our numbers there, we wind up getting 4.423 millihenries. What's the, and so that's our answer for part A. So what's our equivalent reluctance seen by coil B? Yep, R left plus R mid in parallel with R right. Absolutely. And numerically, this comes out to be 1.069 times 10 to the 5 amp turns per Weber. Bless you. And what will L B be? NB squared over RB. Absolutely right. Which comes out to be 374.022 millihenries. That one is significantly larger because there's significantly more turns. And then with, sorry, this is the answer for part B. Now, what is the equivalent reluctance seen by coil C? Yep, so R right plus R mid in parallel with R left, which is the exact same thing as R left plus R mid in parallel with R right. So I'll just write that down. R right plus R mid times R left over R mid plus R left. And it looks like 1.069 times 10 to the 5 amp turns per Weber. And LCC is going to be NC squared over RC. And that comes out to be 2.388 Henrys. Again, much larger than the others because there are much more turns. Okay, so this is the easy stuff. Now we have to do our mutual inductance. Okay, so let me see how much room I have on this page. Enough to get us started. All right. So for us to determine our mutual inductance between coils A and B, we are going to need to determine the magnetic flux passing through coil B caused by the MMF produced at coil A or vice versa. So what I mean by that specifically is we are going to have to analyze one of the two following circuits. Whichever one we choose should give us the exact same answer as the other one. Okay. So this is the first circuit that we could choose, and I'm going to draw on here. This is the flux AB. So this is the flux produced by coil A that will be seen or will pass through coil B, since coil B is over here on the left-hand leg of this thing. So we could analyze that one, or we can analyze this one. I'm going to call this flux phi BA because it is the magnetic flux that was generated by MMFB that is flowing through coil A. Okay. Whichever one we choose should give us the exact same mutual inductance in the end. Okay. So we could choose either, and I would argue that the left-hand one is slightly easier to do, but it's not the one that I'm going to do, because if we look at the right-hand magnetic circuit, that's closer to one of the homework problems that I asked you guys to do that I got questions about. So I'm going to try to kill two birds with one stone and talk about how to analyze this. Okay. So what I'm going to do to find phi BA is effectively I'm going to use voltage division, except that it's going to be MMF division because this is a magnetic circuit, and Ohm's law for magnetic circuits. Okay. So you guys remember how voltage division works? All right. So effectively, what I'm going to do is I'm going to find this MMF, which I'm just going to call MMF X. And then I'm going to divide that MMF by R mid, which will give me the flux flowing down. Okay. So if I lump those two operations together, I would find that phi BA is equal to MMF B multiplied by this ratio. So this is my voltage division or MMF division equation. So I'm trying to find the MMF drop over R mid in parallel with R right. So that's going to look like R mid times R right over R mid plus R right. And I divide this by the total series reluctance seen by MMFB. So that's going to be R left plus R mid times R right over R mid plus R right. So that's my MMF division relationship. So that tells me what that MMF X is. And now I'm going to divide by R mid to get just the flux. Dividing by R mid is the same as multiplying by 1 over R mid, like so. And so now I'm just going to do some simplifications here, right? So this R mid and this R mid cancel each other out. Anybody have a problem with that? Okay. Now, the next thing I'm going to do here is another algebraic step because I am incapable of doing math with numbers, or at least doing it well. And so that R left thing that I have there in the denominator, I'm going to multiply that by a factor of R mid plus R right over R mid plus R right. Okay. So if you're all okay with this step, I'm going to go down to the next page and I'm going to continue on my algebraic simplification thing here. So we're going to have phi BA is equal to MMF B times, and I'm just going to work on the denominator first. So R mid plus R left, excuse me, R right. Not that it particularly matters because they're the same, but I'd rather allow you guys to follow my work better. So that's just me being a jackass and multiplying by a fancy form of the number 1. Here I have R mid times R right over R mid plus R right. And then up here, after my R mids cancel each other out, I have left just R right over R mid plus R right. So the purpose of me doing this fancy hippie algebra here was to put a factor of R mid plus R right in the denominator of everything so that I can cancel it here and here and here. That gives me MMFB multiplied by R right over R left times R mid plus R right plus R mid times R right. Like so. And the last thing that I'm going to do here is simply say what MMFB is. NB times IB. So it's going to look like NB times IB times R right divided by R left times R mid plus R right plus R mid times R right. So we've done 90% of the work here, okay? We're almost done. You're almost done listening to me be a jerk and making you guys do tons of algebra today. All right, so we're 2 steps away from the finish line. What is the flux linkage of coil A? So what is flux linkage by definition? Number of turns times the flux. So if we're looking for the flux linkage of coil A, it's the number of turns in coil A multiplied by the flux that's passing through coil A, which is that phi BA thing we just calculated, okay? Now, this is where we have to pay a little bit of attention, okay? So let me scroll back up here and explain what's going on, right? The flux in general that's generated by MMFB, let's call it phi sub B, is in the up direction, right? And so the part of it that breaks off and flows through coil A is in the down direction like this. The flux that is generated by coil A is in the up direction, right? So our coil A is going to see the flux that's generated by coil A in one direction and the flux that's generated by B but passing through A in the opposite direction. Since those fluxes are in the opposite direction, our flux linkage is going to be negative. If they were in the same direction, like the example we worked earlier, we would have a positive sign there. I just wanted to point that out, okay? So I'm going to throw a negative sign right there because the fluxes are in opposite directions. From here, our mutual inductance, LBA, is going to be our flux linkage, gamma A, divided by our current IB. So that's going to be negative NA times phi BA over IB, or negative NA NB divided by, excuse me, times R right divided by R left times R mid plus R right plus R mid multiplied by R right. And if we substitute in numbers, this comes out to be negative 4.423 millihenries. So calculating mutual inductances is quite a bit more difficult than calculating self-inductance, okay? So what I would like you guys to do for the rest of the class period, all 20 minutes of it, is to work on calculating the mutual inductance seen between windings B and C. And you can use 85% of the work that we've already done. You don't need to recalculate any of the reluctances or anything like that. Really, you just have to figure out how to calculate that flux. And then beyond that point, everything's pretty much the same.